So is my screen visible?
Yes, it's visible.
Okay, okay, thanks. Okay, great. So let us start. So last week, uh, uh, we saw quantum Fourier transform, and it was nicely taught by Muhammad Amir, and we saw the derivation of quantum Fourier transform. We saw how uh, this quantum circuit of quantum Fourier transform is constructed from the derivation, from the mathematical derivation. Then we also saw the Qiskit implementation of quantum Fourier transform. And now, today, we are going to see quantum phase estimation. Tomorrow, we will be seeing the code of quantum phase estimation and a bit of theory. And then we are also going to finish this week the Shor's algorithm. So these two algorithms we are going to cover this week. Tomorrow Shor's and today quantum phase estimation. Then next week Grover search, and next week potentially I will be also taking variational quantum algorithms. So let us start with quantum phase estimation now, and also again this takes the quantum Fourier transform. So we use quantum Fourier transform in this algorithm. Now there are points. So let us start mentioning these important points. Recall that eigenvalues of a unitary matrix, eigenvalues of a unitary matrix U is of unit modulus. And this is in the case of we have already seen. So, like in unitary transformation, we are aware that eigenvalues of that unitary transformation matrix, is of unit modulus, and therefore, so it can be written as e to the power I theta. Why e to the power I theta? Because taking the modulus of e to the power I theta also gives you unit. That means 1. That is why we can write those eigenvalues, we can represent those eigenvalues of the unitary matrix as e to the power I theta. And what is the advantage of doing that? We are able to associate not only a value, but we are also able to associate a phase, right? We are also able to, since it is e to the power I theta, therefore we are also able to take advantage of the complex plane, right? Complex plane values. Remember that Hilbert space supports complex numbers, right? Therefore, we would like to take advantage of that, right? And Hilbert space is a infinite dimensional space. So, therefore, we can write using e to the power I theta, and then goal. Then what happens? Then goal of QPE is to estimate the theta, which is the phase in e to the I theta according to the eigenvalue equation. Okay, eigenvalue equation. So you have already seen what is eigenvalues and eigenvectors. So eigenvalue equation is what? U get psi, where what is eigenvalue equation? Where you have a matrix, and that matrix is multiplied with a vector, and that is equivalent to multiplying that same vector with the eigenvalues of that matrix, right? That is the eigenvalue equation, right? In mathematics, in linear algebra, we have studied that, right? What is matrix multiplied by the vector means that also that vector, it is equivalent to also multiplying that vector with the eigenvalues of that matrix. Okay, it's more like, also multiplying that vectors with the with various factors of that matrix. Okay, eigenvalues, eigenvectors are more like factors of that matrix. Okay, just like we factorize polynomials, like we have a quadratic polynomial. Okay, then we can have a cubic, right, where we see the powers of the variable, right? And we say that when they are the powers is 2, it is quadratic, and 3, it is cubic, and if it is 4, then it is quartic, and so on, right? Like that we follow. So similarly in matrix also, this eigenvalue, eigenvector somewhat like factoring the matrices. Okay, and then therefore we, with that in mind, therefore we can write this as e to the power I theta, or e to the power, if you also include 2 pi I theta or pi I theta, anything, it doesn't changes, because whenever you take the modulo, it comes out to be unity and multiplied with that vector, where now where this part is what, this part is going to be what, eigenvalue, and this eigenvalue which contains the phase. Okay, which contains the phase of u. Okay, so therefore eigenvalues of u has some phase. Why? Because we have chosen the representation to be like that. We know that e to the power I theta comes from the Euler's value. It is Euler's formula, right? E to the power I theta is cos theta plus I sin theta. We know that it comes from Euler's value. And what is Euler's equation? It is this. It is what? It combines the polar polar plane and the complex numbers, right? It combines the complex plane and the polar plane, right? So that is the usage of Euler, right? Right, what is Euler? Very short, like, what is Euler? If you have the complex plane where this is the real and this is the imaginary part, right? So, and if you also have the polar plane means what? The coordinates which are represented by cos theta sin theta, right? In this case, if you draw, if you have a point, then that point can be represented by e to the power I theta, which is equal to cos theta plus I sin theta, right? And it also makes sense because in polar plane, the coordinates are what? Cos theta comma sin theta, right? Like just as in Cartesian, we have x comma y. So therefore, x and comma y are replaced by cos theta sin theta. Cos theta represents the x-axis, that means the base, and sin theta represents the perpendicular, right? Anyways, cos theta is based upon hypotenuse, and sin theta is perpendicular upon hypotenuse, right? So it makes, right, matches. So with that concept in mind, this is the Euler, and that is why it is combining both the planes together, complex plane and the polar plane also, right? Therefore, we are able to, this is how we are able to take advantages of multiple stuff by representing the eigenvalues in the way e to the power I theta. We are able to take advantage of this. So therefore, now we are able to, now what we this algorithm will do is that we are going to estimate this phase, this theta value, which is associated. So QPE algorithm uses two registers. Okay, so by this time you are already aware what are registers, and like, I mean, you have seen Deutsch, Georgia, Bernstein, Vazirani, Simons, then, I mean, several algorithms, right? You have now seen all the algorithms. So now, so where the first register, so what will happen? So first register contains n qubits in state get 0 tensored n. Okay, and what will happen now? we choose this according to the number of digits of accuracy. So basically this first register is chosen in such a way, it is according to our wish, that what is the estimation accuracy we require. So we can write that point here, that we choose this according to the number of digits of accuracy we wish for our our estimated theta, and with what probability we wish the procedure to be successful. Okay, we, and with what probability we wish to. So basically, like, first register determines those stuff. So like, with how much accuracy we want our theta to be determined, and also with the probability with we want the QPE algorithm to be successful. Okay, that's what it means. Procedure to be successful with QPE algorithm to be successful. And then second point is, second register contains the state the eigenvector. Okay, ket size what, the eigenvector, right? Ket size what, this is the eigenvector, right? We have seen eigenvector, this is the eigenvector. Second point is second register. Second register contains the state ket psi, which is which is an eigenstate of our unitary operator. Okay, and that will also be our target, right? So that will be our target, because we are going to apply the unitary operations uh, on this target. So second register is also the target basically, and the first register will have all the controls. So we will see that now. So QPE full circuit. Okay, QPE full circuit. So how will the circuit look like? We have Hadamard. Okay, we will start with Hadamard, right? Again, we have Hadamard, and then so on up to Hadamard. Okay, and then we also have Ket psi. Okay, we also have Ket psi, right? And then we will have these controlled U 2 to the power n minus 1. Okay, then let us draw another one U 2 to the n minus 2, and so on. Okay, dot 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 dot, so on up to U 2 to the 0. Okay, and nothing we do here, nothing. Okay, and then what happens is that then we, after that, we are also going to have here What is this? This will be QFT dagger. Okay, QFT dagger means what? Inverse quantum Fourier transform, right? Which you have seen last week, right? If we can do quantum Fourier transform, that means if we can convert our computational basis to Fourier basis, then we can also come back, right? It is very similar to in the signal processing. You have already studied this, right? If you have not taken signal processing, don't worry. But in signal processing, if you have studied, then you have already this idea that if you have a basis, you can actually convert basis, right? For example, you can go from time to frequency domain, and then again from frequency domain you can come back to time domain, right? For example, you can take any example. For example, Laplace transformation. In Laplace transformation, you deal with the value s, right? Where s is also a complex quantity, and again you can have it in the s domain. So what is the utility, what is the important aspect of Laplace transform? That you are able to convert your complex time domain equations into s domain equations, which are algebraic in nature, right? And algebraic equations are much more easier to solve rather than having partial derivatives, or rather than having derivatives, complex differential equations, basically, right? So that is why Laplace was there, and similarly Z was also there, right? But Z transform is for the discrete and Laplace is for the continuous, right? So in the similar case, since we are able to do that, so here also it is the same thing. Here also, once we apply the Hadamard and once we have these controlled rotations going on, so I will be drawing the remaining circuit. Once we have this control rotations going on, we are actually entering the Fourier basis. Okay, all the computations are done in Fourier basis, and then once the computation is done, you have to go back, right? You have to go back to computational basis and then take the measurement, because the measurement we are doing till now is on the computational basis. Computational basis means cat 0, cat 1, right? So then you have these lines, okay, and then you also have dot dot dot. So like, here also you have lines, okay? So all these lines going, okay, and then also you have line here, and then this is the first, okay, this is the first control, then this is the second one, okay, and so on, okay, like, so on. So this, there will be a third one here, right? There will be a third one. Look at this dot, okay, there will be a third one, okay, then there will be a fourth one, okay, like this. Carefully you can draw this, okay, it will keep on basically, and then finally you will have this one. Okay, so the circuit structure is very similar to what you have seen in quantum Fourier transform, and actually you are going to see that indeed when we want to implement these operations of unitary, you actually apply the same gate. That means the control phasing gate, CP gate in Qiskit, which you have already learned last week in quantum Fourier transform. It's the same gate through which we actually apply these controlled unitary operations. Okay, and then finally, what we are going to do, we are going to take the measurement. Okay, we are going to take the measurement. So this is measurement. Okay, and this is so on. Okay, then measurement again. Okay, and so you are going to get the result here. So what will be the result? It will be 2 to the n theta. Okay, I have written this in decimal notation, so I'm going to write that now. 2 to the n theta means your theta value in decimal, but you are going to, of course, receive that in binary, and then you are going to convert that into decimal in order to find out the value. So let us write that point down now. Okay, that's the circuit. Again, no measurement is done on the second register, as you can see. So what is the first register? First register is what? The above one, right? So this is the first register, right? And all of these start in ket 0 tensor n. That means all these are n qubits which are initialized to ket 0. Okay, and this is the first register, right? This is the first reg means register, and then this is the second register, right? This is, so no space, okay, second register here I am writing. Okay, now note that first register is the, you can give it a name, so this is just a name, counting register of n qubits, which stores which stores the value 2 to the n theta, and second register contains ket psi. Okay, ket psi is eigenvector, right? And also note also that 2 to the n theta is equal to theta 1 up to so on up to theta n base 2. Okay, so 2 to the n theta is decimal, and you are going to get this result. Base 2 means what? Binary. It is binary, right? Now let us try to do the analysis of this circuit. So let us try to, now let us mark the points. Okay, let us mark the points in the circuit. So let us scroll above. Okay, so this is one point. Okay, this is, look at this dotted line carefully. This is the one point, right? This is the first. And then after this, like when you have applied all the control rotations, right? When you have applied, this is the second point of the circuit. And then we have here, what is this? This is the third point, right? Just as we have done for all the other algorithms, Diuchi. So similarly, the same thing. And this is what? This is the fourth step. Okay, this is the fourth step. If you see, it is written here. Okay, this is the fourth step. Okay, fourth step here.
Sir, I have a question. What are
Yeah,
we actually trying to achieve? As you gave eigenvector in the last qubit, now what do you expect it? What do you expect in the result?
the result expectation is 2 to the n theta. You are going to estimate the value of the phase, and the result will be in binary. You are going to convert that and then achieve the result of the phase.
Okay. And so one
You
more
are going
thing,
to
like,
estimate theta. Yeah,
and sir, all the initial values of the first n minus one qubits is zero. If we give it as one, so it will become minus ket minus after Hadamard's. So will it put any difference on the results, final result?
it will not put so much difference on the final result. The result is basically we are going to estimate the theta. The plus minus will not make so much difference because we are going into Fourier domain here in the middle. This is Fourier domain, right? Then we apply QFT dagger, right? And then after that, we are going to achieve computational basis again. So we are going to return back to ket 0, ket 1s after applying QFT dagger.
I mean,
And
there will
then we
be a
take the
complete
measurement.
Hadamard layer in the end of QFT.
There is no Hadamard layer. We are applying QFT dagger circuit, which you have learned last week, and then we directly measure it. No
Okay.
other layer is applied. Yeah. It is a basis transformation, right? Which you have learned in the last week, right? It
So
is
will
the
you be
same thing.
showing the code for this, like how to convert the normal eigen into that last
Tomorrow.
psi one? No, you have to change it to quantum information. No.
Yeah, tomorrow we are going to see the code for this.
Okay.
Yeah, today is theory lecture. Tomorrow we are going to see the code for QPE. The code is also very similar to QFT, which you learned last week.
Okay.
Okay, so let us proceed. So then let us do the analysis. So first step. So again, we are doing like the previous one, step one. Let us take the first step, which is we create the superposition. So let us say that we have these states. Let's put them some name. Let's say we have ket psi 1, and then we have, so I'm going to write a general formula. Tensored n, ket psi is also there. Then step 2. In step 2, what we are going to do, we are going to apply controlled unitary operations. Okay, so let us apply controlled unitary operations, CU, as we have seen in the circuit, right? So controlled unitary operations, which is the CU. So let us write the general equation for CU, Cu 2 to the j. Okay, so applying U2 to the j, this is a general notation. U applied to applied with ket psi. Okay, ket psi is also there, and then we can break it. U2 to the j minus 1 U ket psi, and then once we break it and U ket psi, you already know what that is. So U2 to the j minus 1 e to the power 2 pi I theta ket psi, and so on. We keep on breaking in that format. 2 to the power j minus 1, now it can be broken into again u, and it will become u2 to the j minus 2, and so on. We keep on breaking it in that format, and then in the end, the eigenvalue which we are going to achieve will be 2 pi I 2 to the j theta ket psi. Now once we achieve this, we are going to apply this operation into our value which we have achieved, into our superposition state. So applying n times Cu 2 to the j operation, and also using this identity ket 0 plus 2 pi I theta times ket 1 tensored ket psi, we get now we are going to get the ket psi 2. What will be ket psi 2? Now we have applied n times Cu2 to the j, and we have already seen u2 to the j, and we have broken it down into parts, and we saw what its value is, and we use another mathematical technique, ket 0 plus e to the power 2 pi I theta ket 1 tensored with ket 0, and once we do that, then we receive this equation. Once it is applied, then in the general formatting, this is the generic equation, general format, we receive this ket 0 plus a equation very similar to the QFT equation. Because again, why? Because we are in the Fourier domain. Now we are in the Fourier domain. Therefore, this equation will be very similar to the QFT equation. So therefore, recall the QFT equation from the last week and flip back pages in your notes. You will see the QFT equation, and I am going to point out the difference soon. E to the power 2 pi I theta 2 to the n minus 1. Ket 1 is also there, tensored, And remember, we were able to get an equation very, very similar in the QFT also last week. Again, get 0 and so on. This is a dot, right? E to the power 2 pi I theta 2 to the 1, and it goes till 2 to the 0. Get 1 tensored with the last last value, get 0 plus e to the power 2 pi I theta 2 to the 0, get 1 tensored with get psi. So therefore, in a more concise way, we can write 1 upon 2 to the n summation k is equal to 0 to 2 to the n minus 1 e to the power 2 pi I theta k get k tensored with get psi. But look at the don't look at the compact equation. Look at the other equation. Look at the expanded equation. That expression looks similar to the QFT equation which you have derived last week. I will just mention where k is integer representation of n bit binary numbers. And now that is where the step 3 comes, where we explain. Now observe and match this match the expanded representation. Do not look at the concise notation right now. Look at the expanded equation and compare that with the QFT expression which you have received last week when you were solving the formula of QFT, and compare and observe that psi 2 expression is same as that of QFT with x in QFT. Remember, there was a x in QFT replaced with 2 to the n theta. Therefore, because of this, therefore, we can apply QFT dagger to go back to computational basis. So this is the same thing as we have seen the last week. Once you have, and we have already seen what is a QFT dagger last week through code, and have a look at it again. So it is the same thing here also. We are doing QFT dagger, which you have learned in the last week. We are going back from the Fourier basis. So once we are in the domain of Fourier basis, when we are doing this controlled unitary, we get into this domain of Fourier basis, as we can see from the expression. And therefore, since we are in that domain, therefore we again go back to computational basis by applying the QFT dagger. And therefore what happens, and also the expression is very similar to QFT, where x, we had x in that QFT expression, but it is only replaced with the 2 to the n theta. And you can therefore see the utility of QFT, that with the help of that QFT we are able to estimate this phase by applying this controlled unitary rotations multiple time. And because of, and again I will be explaining that more, because of the phase kickback, you are able to store the phase value. Okay, so first let us complete the steps, then I'm going to explain that. So get psi 3 is equal to, again, we are going to write the same equation. K is equal to 0 to 2 to the power n minus 1 e 2 pi I theta k, get k tensored at psi, and we apply the QFT dagger, and we are able to get, so we apply the formula of QFT and dagger, and once we apply, then you are able to get this x is equal to 0 to the n minus 1 summation k is equal to 0 to the n minus 1, and e to the power, there is a sign difference in when you apply QFT dagger, as you might have studied last week, 2 pi I divided by 2 to the n, and we get x minus 2 to the n theta. Here, get x tensor with get psi. Okay, this is get psi. So since there is no space, I will write it here, get psi. Now, once we go back here, after that, what we have to observe, now observation has to be made. So step 4 is again about having this observation note. Now note that, and this has been proven by taking a lot of experiment, note that get psi 3 will peak near to the n theta. So now, with a lot of experiments, it has been seen that once it is converted, and then once you take the measurement, after the measurement, the value which you are going to receive in the first register will peak near 2 to the n theta. Peak near 2 to the n theta means, that means you have a more probability of finding 2 to the n theta. That means your phase value. Okay, you have more probability of finding phase value, but there are two conditions. What are those two conditions? If 2 to the n theta is an integer value, let's say, then with high probability we obtain, then with high probability we are going to obtain 2 to the n theta in the first register. But if 2 to the n is not an integer, if 2 to the n theta is not integer, then also it has been found, and there is a paper available on the Qiskit textbook as well, which shows then also that the value of ket psi 3, once you take the measurement, will peak at x is equal to 2 to the n theta with probability, with a probability better than 40%. So both the cases, in both the cases, you are able to estimate your phase when it is not an integer, then definitely the probability of occurrence of your estimated theta is less. But it has been shown that still it is able to perform better and give you 40% result. And also this algorithm has another specialty, that this algorithm is not very NISQ friendly, right? This algorithm is not so much NISQ hardware friendly. NISQ means noisy intermediate scale quantum. That means this algorithm works very well for perfect quantum hardware. That means you need to have perfect qubits, a fault tolerant quantum computer. There, the QPE algorithm is going to do wonders, not with the NISQ quantum hardware which we have today. Therefore, and that is why there are variations of this algorithm which you will be able to find in the literature, which are variational algorithm, which we are going to see next week. And that is why we go towards, this is the why we go towards variational quantum algorithms, because those algorithms are much more robust to noise which is in the NISQ devices in our current quantum hardware. Now for the explanation, QPE uses the phase kickback to estimate the phase of U in n qubits. This means that the phase of the U gate or some U transformation, some unitary transformation is kicked back to the qubits in the first register via the controlled operation, and then this kicked back this kicked back phase rotates the first register qubits to estimate the phase of U gate. Okay, it will be able to estimate the phase of U gate because of the phase kickback. Therefore, from the target where we are applying 2 to the j operations, from the target, the phase is kicked back into the first register via the controlled operations. Therefore, the phase value is slowly pushed back into all the n qubits gradually, and all those n qubits rotate in such a manner that once you do the QFT dagger and once you take the measurement outside, it indeed gives you the result of 2 to the n theta. That means your estimated phase value because of the operation of, because of the mechanism of phase kickback. Therefore, repeating the CU appropriate number of times encodes theta as a number between 0 and 2 to the n in Fourier basis. Therefore, repeated application of CU appropriate number of time encodes the value of theta gradually inside all the n qubits through the mechanism of phase kickback in the Fourier basis as a value between 0 and 2 to the n. And therefore, once we apply QFT dagger, you get into computational basis, and once you take measurement, you are able to peak near 2 to the n theta. That means have 2 to the n theta. That means your theta, estimated theta value with the maximum probability. So what can be one example? So e.g., an example, small example, let's say you have the unitary. So let us say we have all the quantum gates. We have already studied all the quantum gates, and you know that all the quantum gates are unitary transformations. So let us take a phase gate, which we have. You can take Z gate, you can take S gate, right? You have phase gate. Z gate is also a phase gate, right? S gate is also, T gate is also, right? So let us take one example. Let's say we have T gate. So let's say T is applied to ket 1, because if T is applied to ket 0, then nothing happens, right? So therefore we apply it, because T when applied to ket 1 gives you the phase value, right? EI pi by 4, right? That is a T gate, right? EI pi by 4. Yeah, that value gets attached with ket 1, right? So let us say let us write it in the general format, 2 pi I theta and ket 1. Okay, so this is from where do we take this? We take this from this. U ket psi is equal to e to the power 2 pi I theta ket psi. So in this case, ket 1, ket psi is what? Ket 1, right? And u is what? U is T. This is an example, okay? U is what? U is T. And from this, you can already see that it will be, since it is what? What is T? T is what? When T is applied to 1, what it gives you? It gives you e to the power I pi by 4, right? E to the power I pi by 4. It attaches with the ket 1 value, right? That is the, and when you apply T to ket 0, then nothing happens, right? You get ket 0 back, right? That is a truth table, right? If you do not recall, please look at your notes before in the single qubit section, right? Which you studied 1.5 months back. Okay. So therefore, that means that 2 pi I theta is equal to I pi by 4, and now we are able to extract theta from here, right? So if you solve this, you see that theta is equal to 1 by 8 value, and from this you are able to extract the value of the theta. We are going to see this more tomorrow, then it will be much more clear how we are doing this calculation and estimating the phase. But if you recall, T gate is also known as the pi by 8 gate, and it proves that, as you can see, theta is indeed 1 by 8, and that is why T gate is also known as a pi by 8 gate. You can check your notes now, and you can say indeed that is the case. T gate is also known as pi by 8 gate. Now, just to mention for completion, what are the applications of QPE? So QPE utilizes QFT, that we have definitely seen, because it works in the middle of the circuit. It is completely in the Fourier domain due to controlled phasing operations we are going to see tomorrow, and then it will become more clear. So therefore, several applications, a few applications of QPE. The first can be factoring, because this is used in Shor's algorithm. Factoring, okay, order finding, and then second can be quantum random walks, and third is for linear system of equation. So QPE has several. So basically, QPE cannot be used individually as something. QPE is used as a subroutine of an algorithm. That means QPE is inside a more bigger circuit. The bigger circuit could be of some particular application. Let's say quantum finance. In quantum finance, you are solving for some linear system of equations. So the algorithm will be much more bigger, but this will be a sub algorithm, a sub part of that major, of that bigger algorithm. Okay, so This concludes quantum phase estimation. And if you have any doubts, please go ahead. Yeah, any doubts? So are there any doubts regarding quantum phase estimation? So we have seen how it uses QFT, and we have seen what is phase kickback. Yes, ma'am.
No, sir, no doubts. Thank you.
No doubt, it is clear, right? So it is very similar to QFT, which you have learnt last week.
Yes, yes. Yeah.
Okay, okay. Thanks. So I will stop sharing, and I will also stop recording at this point. And we have seen the theoretical part of QPEE, and now tomorrow we are going to see the Qiskit implementation that will bring more clarity. And then we are immediately going to get started with Shore's algorithm tomorrow.